All right, welcome back. So remember from last lecture that we wanted to solve a generic system of differential equations x dot equals ax, where x is a vector and a is a matrix. I've stopped drawing underbars to denote matrices and vectors. I hope you know that x is a vector and a is a matrix. To solve this generic system x dot equals ax, what we're trying to do is diagonalize it, which means we want to find a new coordinate system, a change of coordinates into a new coordinate system z, so that z dot equals a diagonal matrix times z. Because it's much, much easier to solve this differential equation where d is diagonal than this differential equation where a is kind of a generic gnarly matrix. And so we're literally trying to find this matrix T that is a change of coordinates between x and z, where it makes my dynamics easier. We're trying to find that coordinate transformation T. And in the last lecture, I showed that the matrix T that diagonalizes my system is specifically the matrix T from this eigenvalue problem. And so in this expression, A is my original matrix, T is a matrix of eigenvectors of A, and D is a diagonal matrix of eigenvalues of A. So I'll just write this out. So these diagonal entries are eigenvalues. This is a German word I'll tell you about in a minute, eigen. And the columns of T are my eigenvectors. And so instead of thinking about this as a matrix eigenvalue problem, it's sometimes a little easier to just think about finding individual eigenvectors and eigenvalues one at a time. So kind of columns of T and entries of D, finding those one at a time. And so the way I'm going to write that is this ax equals lambda x. Okay, so the German word eigen literally means like special or characteristic. It actually, in German, it means latent or characteristic. I'm going to write this down. So like eigen means latent or characteristic. What that means is kind of like the essence of. It's the essence of something. So if you like boil off everything else, the latent or the characteristic part is what's going to remain, the eigen part. So you'll notice my channel is called Eigensteve. I'm Eigensteve. Eigen just, and also I guess when I think of eigenvalues and eigenvectors, I'm thinking these are kind of special values and special vectors. I'm going to define what I mean by special in a minute. But ax equals lambda x for special vectors x and for special values lambda. And that's kind of what I mean, is that these x are going to be eigenvectors. Those are special values, special vectors where this is true, and lambda are special numbers where this is true. Not all lambda are going to satisfy this equation, and not all vectors x can satisfy this equation. Only very special vectors x and special vectors lambda can satisfy this. Good. And this is the eigenvalue equation for a single pair x comma lambda. So this is the eigenvalue equation for a specific pair, for a pair of eigenvalues and eigenvectors, x comma lambda. So they always come in pairs. An eigenvector always has an eigenvalue associated, and an eigenvalue always has an eigenvector associated to it. Okay, so this is what I'm going to talk about today in this lecture. I'm going to give you some numerical, not numerical, by hand examples. We're going to actually compute these special vectors x and special values lambda for a particular A matrix that I'm going to write down. And then we're going to talk about how to compute these in general for an arbitrary matrix A. Now, what I want you to notice here is that my definition of special is pretty easy to understand, I guess, is what I want to say. What I mean by special is that there are special vectors x that when I multiply them by this matrix A, the direction of x doesn't change, it just gets scaled up or down by lambda. So what I mean here is that multiplication by a matrix, I usually think of that as a coordinate transformation. So vectors, when you multiply them by matrices, typically they'll rotate and maybe stretch and they deform. So you can take all of your vectors in x, and when you multiply them by A, it's going to kind of rotate and deform generically those vectors. And there are some very special vectors x that when you multiply them by A, they don't rotate, they just get longer or shorter. And that's what I mean by these eigenvalues and eigenvectors. So that's the example I'm about to show you. Maybe I'll move my notes over here so I have some room. So let's just do an example to get some intuition, and then we'll talk about this in the generic case. So an example, A matrix, I'm going to pick an A matrix that is 3, minus 1, minus 1, 3. 3, minus 1, minus 1, 3. Just a little simple 2 by 2 A matrix, but it's not diagonal, so it's going to be difficult to solve differential equations with this A matrix. And so what I'm going to do is I'm just going to try like a random x vector. I'm going to just pluck an x vector out of a hat, multiply it by A, and see if it satisfies this equation. Okay, so we're going to try, let's try x equals 1, 0. That's kind of the easiest thing we can try. Let's try x equals 1, 0. And I'm trying to think of how I want to draw this, because I'm going to draw you a picture. But let's try x equals 1, 0. Then ax is going to equal, I literally can just multiply a times x, and it's going to be 3, negative 1. This is 3, negative 1. OK, and clearly you can see that a times x is not just x times some number. It's not just x longer or shorter. They point in different directions, completely different directions. So I'm going to draw a picture, and I want to be very careful about what colors I use. Otherwise, this is going to get impossibly messy. So let's say I have my x1 and x2 axes here. And my first test vector, maybe I'll draw some ticks, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. I could do this in a computer, but I think it's way more fun to do it by hand. This is how I always think about it. So what I literally did here is I took this test vector x, this vector 1, 0, it's 1 in this direction, 0 in this direction, and I multiplied it by a, and I got something that was 1, 2, 3, negative 1. So I got something that points in a completely different direction. This was x, and this was a x. They point in completely different directions. So they can't possibly be eigenvectors or eigenvectors of this system. Good. Let me try one other example just to illustrate. Let's try x equals 0, 1. So now instead of pointing in the x direction, it's going to point in the kind of the x1 direction. It'll point in the x2 direction. Again, I can multiply this by a, and I get ax equals. Now it's going to be negative 1, 3. So that's negative 1, 3. That means that I'll pick a different little color here. I'll just do yellow because they're kind of pretty similar, yellow and green. So now this little vector here multiplies to negative 1, 1, 2, 3. Again, these are pointing in different directions. So my vector rotated after multiplication by a. And so neither of these kind of principal x1 or x2 directions are eigenvectors of my A matrix. These are not eigenvectors. So there are special vectors I haven't convinced you yet probably that there are in fact these magic vectors where this is true. So what I'm going to do is I'm actually just going to write them down. I'm not going to derive them yet. I'm just going to write them down, show you that they have this property, and then I'm going to show you how to solve for them if you had this A matrix. And I'm going to do this in blue and pink. So the first special value is, I'm going to claim that the first special, and sometimes I call my eigenvectors xi. Sometimes I like to use my fancy pants xi vector here because I really like xi. Xi and I are old friends. And the first eigenvector is going to point in the 1, 1 direction. Okay, this is, I claim, an eigenvector. Let's see if this is true. So I'm going to multiply this by A. I'm going to take A times xi. What happens when I multiply A by 1, 1? I get 3 minus 1 is 2, and minus 1 plus 3 is also 2. So this equals 2, 2. And lo and behold, this actually is in the same direction as xi. It's exactly 2 times bigger than xi. It stretched xi by a factor of 2. So this is my lambda 1 equals 2. Okay, so A times xi is equal to 2 times xi. That's good. So I'm going to draw this picture. So this vector here in the 1, 1 direction, this xi is an eigenvector because when I multiply it by A, I get a vector in the exact same direction. A times xi1 equals 2 times xi1. This was xi1. So that's really, really special. That's what I mean by an eigenvector. They are special kind of magic directions where if I take a vector in that direction and I multiply it by A, that vector stays in that direction. Very, very interesting, very, very important. And you can almost picture how those special directions where if I multiply by A, things stay in that direction. That's how I'm going to decouple my dynamics, because in these directions, my dynamics are completely decoupled in this direction and in the other direction. I'll get back to that later. So that's one special eigenvector, xi. The next special eigenvector, my next special xi2, I believe it's going to be like 1 minus 1 or something like that. So it's 1 minus 1. I've had a lot of experience with eigenvalues and eigenvectors. Almost you can read these off of a 2 by 2 matrix, but you'll get there if you can't do that already. Let's multiply A by this now. And so now I'm going to multiply it, and I get 3 minus minus 1 is 4. And minus 1 minus 3 is minus 4. So I get 4 minus 4. Again, this is just a constant scaling of xi2. Sorry, I should have written that this is A times xi2. And that's what this 4, negative 4 is. And so my lambda 2 equals 4. Okay, so I can again draw this one. So I take a step 1 in the first direction and minus 1 in that direction. That's xi2. And if I multiply it by A, I take 1, 2, 3, 4 steps, 1, 2, 3, 4 steps. And this is A times xi2, and that just equals 4 times xi2. So there are, in fact, these very special kind of eigendirections, these eigenvectors x, I call them xi1 and xi2 here, these pink and blue directions, where if I multiply those very special vectors by my A matrix, I get a vector in the same direction that's just scaled by lambda. In this case, lambda 2, in this case, lambda 4. Okay, and I think I showed you and I convinced you if I just randomly pick a vector and I multiply it by A, it's going to rotate. It's going to go into a different direction. So not all vectors x are eigenvectors. Only very special vectors are eigenvectors that have this property. Good. Okay, so there's exactly 2 eigenvalues and 2 eigenvectors for this 2 by 2 system. I'm just telling you that's true right now. We'll see that that's true in a minute. Okay, there's exactly 2. There's 2 kind of eigen vectors and values. Good. And again, they come in pairs. This is the eigenvalue corresponding to this eigenvector. And similarly, this is the eigenvector corresponding to this eigenvalue. They come paired up. That's why I color-coded them. Okay, good. So hopefully this builds your intuition. Now what I'm going to do is, this is just one example for one A matrix. That's not that generic. So now what I'm going to do is I'm going to show you how to solve for these eigenvalues and eigenvectors for a generic matrix. Okay, so now we're going to go and how to do this in general. So I'm going to erase all of this, and then we're going to work that out. Okay, so I've given you some examples of eigenvalues and eigenvectors. Now I'm going to show you how to solve for them in general. Someone gives you a random A matrix. You're going to be able to figure out what are the special x and lambdas that are eigenvalues and eigenvectors. So I'm literally going to take this equation here, and I'm just going to rewrite it a little bit. So I'm going to say that, and I want to give myself a little space here. I'm sure I'm going to need it. So I'm going to say that A x equals lambda x. You can always do this with matrices. You can say that lambda, just a number times a vector x, is the same as that number lambda times the identity matrix times x. Because any vector x is just the identity matrix times that vector x. So I can pop in a matrix I here. If you are confused by that, pause. And write this out with an identity matrix times x and convince yourself that that is exactly just x. It's totally fine. And so essentially now I can move this. The reason I'm doing this is because now I can move this over to the left-hand side, and I have matrix A, matrix lambda I times vector x. So I can move this over to the left-hand side and say A minus lambda times the identity matrix x equals 0. This is equivalent to my eigenvalue problem here. This is an equivalent way of writing it. And again, x is a vector, 0, it's a vector of zeros. A and I are matrices. I'll just put them here so you remember. And lambda is a number. And so what we're trying to do is we're trying to find x and lambda, pairs of x and lambda that satisfy this equation. Now, you might imagine, well, this is easy. I'll just make x equals 0, and then this is always true. That is technically mathematically true, but that's kind of boring. It's not really a vector. X equals 0 is not a vector. It has 0 length. And so I'll just write down, case 1, x equals 0 is kind of a solution, but it's not very interesting. It's not what we're looking for. Interesting. These are not the droids you're looking for. Okay, not the eigenvectors you're looking for. Case 2 is more interesting. So case 2, the other way that this can be equal to 0 is for x to not be 0 and for this matrix to be what's called singular, meaning it maps certain vectors to 0. Okay, I'm going to write this out and then I'm going to explain it. So case 2 is where x is not 0 and the determinant of A minus lambda I equals 0. If the determinant of A minus lambda I equals 0, that means there are some directions where this matrix will map those directions to 0. Okay, I'll draw you a picture later, just take my word for it for now. That's what this means, is that if I have a matrix A minus lambda I with determinant 0, there are certain subspaces, certain directions, that if I multiplied them by that, I would get 0, which is kind of what I'm looking for. I'm looking for an A minus lambda I where there's directions that map to 0. Okay, so that's kind of what I'm looking for. In this case, we call this singular. We say A minus lambda I is singular. I put my air quotes on the wrong thing. A minus lambda I is singular. That's just the words we use in math to describe this. And that means, meaning it maps some vectors to 0. Okay, to the kind of 0 origin point. I'll convince you that this is true in a minute, just bear with me. And so this expression here, this determinant of A minus lambda I equals 0, this is not true for all lambda. Remember, I showed you in a couple of lectures ago that this is actually the characteristic polynomial of our differential equation. This is a polynomial equation, a polynomial equation in lambda, and the roots are my eigenvalues, my eigenvalues. So the first thing I do is I literally, this is something I can write down. I can write down A, I can write down lambda I can write down this determinant, set it equal to 0, I get a polynomial in lambda, and I solve for those lambdas where this is true. For those very specific lambdas, if I have a 2 by 2 A matrix, I'll have 2 of them. If I have a 3 by 3 A matrix, I'll have 3 of them. For those very specific lambdas, then there are some x's that will map to 0. Okay, so, and I'll just remind you that this is, in fact, exactly the characteristic equation when we're talking about differential equations. Characteristic equation when we're talking about differential equations. Okay, good. So I'm just about to, I'll show you how this works on that previous example, on that 2 by 2 system example. But I want to remind you how to compute the determinant of 2 by 2 and 3 by 3 matrices and things like that. So maybe the first thing I want to show you is that the determinant of a matrix A measures the volume of a square after you map it through A. So how do I want to say this? This measures the volume of a unit cube, after all of the sides get mapped through A. After all sides are mapped through, I'm going to draw you a picture, don't worry, through A. So specifically, if I take like this example of A equals 2, 1, 1, 2, really simple A matrix, what I mean by a unit cube is I literally take a little unit vector in the x1 direction, this is x1, and a little unit vector in the x2 direction, and I say that this is a little, you know, in 2 dimensions it's a square, in 3 dimensions it's a cube, in 4 dimensions it's a hypercube. So I take this, you know, square in 2D or a cube in ND, and I map each of those legs through this A matrix. So my 1, 0 leg gets mapped to 2, 1. So that goes from here to here. So this little leg gets mapped here. Okay, this vector gets mapped to here. And this little vertical vector, 0, 1, 0, 1, gets mapped to 1, 2. I take 1 step over and 2 steps up. And this is that vector there. And you could also take this little far corner here and map it through, and you'll find that you get this kind of parallelogram. And I drew a really bad job of that parallelogram. Let's see if I can make this not so horrible. I'm not a perfectionist, but I do have standards. Okay, that's better. And so now, if my original unit square or cube had area 1, because it had length 1 on all sides, the area or volume of this pink deformed parallelogram is going to equal the determinant of A. And for a 2 by 2 matrix like this, the determinant of A is going to be the product of the first main diagonal minus the product of the second diagonal. So that's 4 minus 1 equals 3. So the area of this pink parallelogram is equal to 3. It's equal to the area, the determinant of this A matrix. And so this is kind of how I want to convince you that when this thing has determinant 0, it's singular. It means that I map some directions to 0. What is the only way that I could map this little yellow square here to something with 0 area? The only way I could map it to something with 0 area is if these vectors map to something parallel. So this squished together and had 0 area. And what that means is that the only way that these two vectors, this two-dimensional space, can map into a one-dimensional space with 0 area is if there is some direction that maps to the origin, that maps to 0. Okay, that means there's some direction that's getting collapsed and kind of smushed out of this to give this 0 area. So when my determinant is 0, that means that there are some directions that are being obliterated. Then a times that direction will equal 0. Some directions are getting obliterated. I'm losing dimensions. I'm going from 2 dimensions to 1 dimension. That's the only way this thing could have area 0, is if it's kind of one-dimensional and infinitely thin. And so that's what I mean here when I say that this matrix has determinant 0. There are certain directions, certain x's that get obliterated because this thing has area 0 when the determinant is equal to 0. I'll show you how to take the determinant of a 3x3 matrix because I think that's important for you to know. So det of a 3x3 matrix when I have, let's say, B11, B12, B13, B21, B22. I'm going to stop talking. B23. I'm not going to stop talking, apparently. OK, so the way you take this determinant is, again, similar to this one. I'm going to take the first element times the determinant of the 2x2 block where you omit the first row and column that this B11 is in. So that's B11 times the determinant of this thing, which is B22, B33 minus B23, B32. OK, there's that one, minus this guy times the determinant of its subblock if you omitted that row and that column. So that's B12 times B21, B33 minus B23, B31. And then finally plus, let's pick a different color, maybe I'll do orange, plus B13 times the determinant of this 2x2 subblock that you get when you omit this row and this column. And that's B21, B32 minus B22, B31. Okay? And if I had a generic n by n matrix, I do the exact same thing, and it's recursive, and it's horrible. You take this one times this subblock, minus this one times this subblock, plus this one times this subblock, minus this one times this subblock. And then for those subblocks, you'd have to do the same thing recursively, and it becomes a real mess. But this is it for a 3x3 matrix, and for a 2x2 matrix, it's trivial, just product of the diagonals minus product of the off diagonals. Okay, so that is what you need. You need to be able to compute these determinants of these a minus lambda i's to get a polynomial. It's going to be some big nasty polynomial in lambda, and then you're going to solve that polynomial for its roots, the lambdas that make that equal to 0. Those are your eigenvalues. Then we take those eigenvalues, plug them into here, and find out which x's get obliterated, which x's map to 0. Those are your eigenvectors. Okay, I'm going to erase some stuff, and then we're going to do an example, the exact same example we did last time, so just stay put. Okay, we're going to now solve for the eigenvalues and eigenvectors for that same little 2x2 A matrix we worked on before. So our example is A equals, I think it was 3 minus 1 minus 1, 3, 3 minus 1 minus 1, 3. The first thing we do is we compute a minus lambda I, take its determinant, and solve that characteristic polynomial. So a minus lambda times the identity is easy. This is just 3 minus lambda minus 1 minus 1, 3 minus lambda. Taking its determinant, det of a minus lambda I is just the product of the diagonals minus the product of the off diagonals. So this is lambda squared minus 6 lambda plus 9 plus another 1. So plus 10. Just slow down and confirm that that's true. And this has to equal 0 for my eigenvalues. And so now you see that this is actually just a simple polynomial equation. So I can, did I do this right? Nope, I totally didn't do this right. That was 9 minus a plus 1, which is minus 1, so this should be an 8. Okay, that should be an 8, so this is plus 8, and this is going to be a lot easier for me to do in my head. So now I factor this thing, and this looks like lambda minus 4 times lambda minus 2 equals 0. Just confirm that lambda squared minus 6 lambda plus 8, good. And so lambda equals 2 and lambda equals 4 are my eigenvalues. Good, okay, we're cooking with fire. Now for lambda 2 and lambda 4, I'm going to find the x that gets mapped to 0. Those are going to be my eigenvectors. So this is pretty easy. Okay, so let's just do this. Lambda 1 equals 2. Let's start with lambda 2. So now I take a minus 2I, which is a minus 2I is just 1 minus 1 minus 1, 1. And I'm trying to find the x vector that gets mapped to 0 through that mapping. So I have 1 minus 1 minus 1, 1 times x1, x2. Okay, that's going to equal x1 minus x2 and minus x1 plus x2, and clearly if x1 equals x2, both of these equal 0. So x1 equals x2, x1 and x2 could just be equal to 1, 1. Okay, so that's an eigenvector. I went a little fast, but I think you can convince yourself. I tried to find the x that would map, for x1 equals x2, this maps to 0 if x1 and x2 were equal to each other. Okay, that's what I do here. Similarly for lambda 2 equals 4. A minus lambda 2 minus 4i. A minus 4i is minus 1 minus 1 minus 1 minus 1. Ooh, that's a nasty one. And minus 1 minus 1 minus 1 minus 1, very negative. That equals, minus x1 minus x2 minus x1 minus x2. And so clearly here, as long as x2 is the opposite of x1, both of these will equal to 0. This will equal 0 if x2 equals minus x1. And so I can say that x1, x2 equals, 1, negative 1 is an eigenvector. So this is an eigenvector corresponding to lambda 2, and this is an eigenvector corresponding to lambda 4. And these are exactly the same eigenvectors. This is, xc2, and this is xc1 that we found before. Okay, good. That's everything I wanted to show you. That was a big lecture. We derived how to find x and lambda to satisfy this eigenvalue equation. They are special vectors x and special numbers lambda, so that if I multiply that vector by a, it doesn't rotate or change directions. It stays in exactly the same x direction, and it gets scaled bigger or smaller or maybe even flipped negative by my eigenvalue lambda. And I showed you some examples of how to do this. In the next lecture, we're going to use what we learned here and go back to solving ordinary differential equations. Thank you.